Actually, this video is a continuation to the previous one, that is group theory part 1. You will see at the end of that video, the video stopped abruptly because of some technical issues, and also I haven't edited that video. Okay, so from question number 6, let us start again. So here you can see, as the question tells us, that we have to show that the set of nth roots of unity is a finite abelian cyclic group with multiplicative composition. Nth roots of unity it is. So what is the meaning of nth root? You can understand, if we want to write x cube equals to 1, that stands for cube roots of unity. So simply if we consider x to the power n equals to 1, from where you can easily get x is equals to 1 whole to the power 1 by n, that is nothing but nth roots of unity. So if you want to solve for the value of x, you will get technically n number of values. That's why the name suggests nth roots of unity. And why we are saying unity? Because x to the power n is equals to 1. So whenever we are considering the solution of this type of problem, we need to find out the value of nth root of 1. So nth root of 1 can be written as what? 1 plus 0 into I whole to the power 1 by n. Using trigonometry, you can write cos 0 plus I sin 0 whole to the power 1 by n. So that cos 0, in general sense, by using the general value, you can write cos 2r pi plus I sin 2r pi whole to the power 1 by n, where r belongs to I. Now, with the help of this structure, using De Moivre's theorem, you can write cos 2r pi by n plus I sin 2r pi by n. Obviously, what is the value of r? R should be 0, 1, 2, dot 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 n minus 1. That means you can put r is equal to 0 to get one value of this structure, r equals to 1, r equals to 2. In this way you can carry on up to r equals to n minus 1, so that you will be able to get total n number of values. Now we also know e to the power I theta is equals to cos theta plus I sin theta. So this part can be rewritten as e to the power 2r pi into I whole divided by n. Now first we need to find out all possible structures by putting r equals to 0, 1, 2, 3 dot 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 n minus 1. If you put r is equal to 0 here, you will get e to the power 0 by n, that means 1. If you put r is equals to 1, it will be e to the power 2 pi I by n. Put r equals to 2, e to the power 2 into 2, that is 4 pi I by n. In this way, if you put r is equals to n minus 1, the result will be e to the power 2 into pi into n minus 1 into I by n. In this way you can carry on. Okay, it is 2 into n minus 1 pi I by n. So practically you can consider all these values under a set. So I have considered that set as G. So you can see all the elements of G are listed as follows: 1 e to the power 2 pi I by n, e to the power 4 pi I by n, dot dot dot, like this. Now we need to check whether this structure forms an abelian group or not. Now here you can see there is an additional term, cyclic group. So I am not explaining what is the meaning of cyclic group right now. At the end of the solution I will try to explain a little bit, because cyclic group is a different portion. I will discuss it later in the class. Now G intentionally can be rewritten in this form: 1 omega omega square dot 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 omega to the power n minus 1. Why? Because for simplicity I have taken omega is equals to e to the power 2 pi I by n. Now you can easily understand, if I want to find out omega square, what will be the value? E to the power 2 pi I by n, its whole square, so that means e to the power 4 I pi by n. Similarly, omega cube will be what? E to the power 6 pi I by n. So that's why all possible elements can be listed as 1 omega omega square dot 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 omega to the power n minus 1. Now first let us consider two elements taken from G. Both a and b must be nth roots of unity, so we must satisfy a to the power n is equals to 1, b to the power n equals to 1, so that a b whole to the power n, this part is what? Whenever we are considering this one, actually you can choose any two elements. So ab whole to the power n will also be equal to what? Because you have taken both the elements taken from G, so ab whole to the power n can be intentionally written as what? A to the power n, b to the power n, and that's why you can see it is also equal to 1. So ab is also an nth root of unity, and consequently ab is a part of G. So technically G is closed with respect to the multiplication. Now because we know the product or multiplication for complex numbers is associative and this is a hereditary property, so we have nothing to prove. Again, what is the identity element? 1 can be considered as the multiplicative identity, because 1 into a, where a belongs to G, you can see can be written as a, also a into 1 that is also equals to a for all a belongs to G. So left identity and right identity both should exist. Now finally we have to verify the existence of inverse element. Initially we have seen for 1 belonging to G, 1 into a should be equal to a. Now if possible, let us consider certain element taken from G. What is that? Omega to the power r. Now we all know power of omega varies from 1 to n minus 1 in general. 1 can be considered as omega to the power 0, that is another thing, but in general you can say for non-identity elements, non-identity element means except 1, all other possible values of omega in terms of powers can be a variable quantity that ranges over 1 to n minus 1. So we can say if we take omega to the power r be any other element taken from G, then r should vary between 1 to n minus 1. Now omega to the power n minus r can also be taken as another element taken from G. So if we operate omega to the power n minus r into omega to the power r, then the result is what? Omega to the power n, that should be equal to what? 1. Because you can understand, if I operate omega to the power n, it will give you e to the power 2 I pi by n whole to the power n, that is e to the power 2 pi I. Then cos 2 pi plus I sin 2 pi, which ultimately gives you 1. So here you can understand omega to the power n minus r, as you have seen, it has been operated from the left hand side. It is the left identity, and in a similar manner we can also show it is the right inverse. It is the left inverse as well as it can be shown omega to the power r dot omega to the power n minus r, that is also equal to 1. That means it can be proved in a similar manner. It is also the right inverse of omega to the power r. So here you can say G comma dot is a group. That means G is forming a group with respect to what? With respect to multiplicative as operation. Now we can also understand, if we want to take the product of any two complex numbers, that means z1 into z2, trivially that can be written as z2 z1. So multiplication of complex numbers is also commutative. So we can also say the set of nth roots of unity is also a finite abelian group. Now why we can say it is a finite abelian cyclic group? Because you can see all possible elements can be expressed with the help of omega, but taking different powers. We can say all elements can be written as omega to the power 1, omega to the power 2, omega to the power 3, dot omega to the power n minus 1, and also 1 can be expressed as what? Omega to the power 0. So whenever a certain element, whenever in a certain group, each and every element can be expressed as some integral power of a particular element, you can say that group is a cyclic group. Here you can see all possible structures belonging to G can be expressed by means of omega to the power something. So in that case you can say G has been generated by omega, and because G is generated by omega, that means all elements of G can be expressed by means of integral power of omega, and so you can say this is nothing but the generator of this group. And if there exists a generator for a certain group, then that group is nothing but a cyclic structure, and because of this reason we can say this particular structure G is nothing but a cyclic group of order n. Why it is this is a group of order n? Because you can see how many elements are there. Omega to the power 1 to omega to the power n minus 1, total n minus 1 number of elements, and omega 1 can be written as what? Omega to the power 0, so total n number of elements are there. So that's why it is a group of order n with respect to multiplicative operation. In the later on you will see in some other classes I will discuss about cyclic group, but simply for now you can remember, whenever each and every element of a group can be expressed by means of some integral power of omega, or by means of some integral power of that structure, of that element, of that set, or of that particular algebraic structure, you can say that will be a cyclic group. For example, you can also say, if I want to write say 1 minus 1 I minus I, you can understand, if I want to write I to the power 1, that is also equal to I square, that is minus 1, I cube, that will be minus I to the power 4, that is 1. So technically 1 can be written as I to the power 4, minus 1 can be written as I square, I to the power 1 is I I square I cube is equal to minus I. So all elements can be written by means of some integral power of I. So you can say S is generated by I. So this is also a cyclic group. Remember, in the class I also discussed this particular structure is also forming a group with respect to usual multiplication.